Okay, so today we're doing number 26. It is a standard deviation problem where we have a bunch of bolts and they're produced by a certain machine with a certain average. So the diameter for the bolts is on average 40.42 inches. Some of them are off a little bit. The standard deviation is 0.08 inches. What percentage of the bolts will have a diameter that's greater than 0.37 inches? Okay, that's a really good standard typical problem. So let's see how we would tackle that. First thing I would do is I would imagine that because it says normally distributed, that tells me that we're going to be able to use all our normally distributed machinery and techniques and theorems that we have. It also tells you that it's nicely bell-shaped curve for the distribution with an average here of 0.42. We could call this thing about, I don't know, the X bar axis or the X axis, and that number right there is called X bar. And because it's normally distributed, we know that half of the bolts are over here, bigger than 0.42, and half of them are over here together under the curve. This represents 100% of the area. What this is asking is, and it also tells the standard deviation is 0.08, so I would write standard deviation is equal to 0.08 here, just so I don't forget. Then it's asking, I'm going to try to change this question. What percentage have a diameter greater than 0.37? I'm going to turn that question into an area question. So I'm going to try to find that spot on the number line. 0.37 would likely be left of 0.42, obviously. So 0.4, that would be somewhere around here. 0.37 left of 0.42. What percentage? Well, the percentage could be represented by the area to the right of that. Well, that's not the color I want, sorry. So there you go. With the question, what percentage is answered by this area? So that if we could answer the question, what percentage of the area lies to the right of here, the shaded area, that would be exactly the percentage of the bolts that have a diameter greater than 0.37 inches. Okay, so you could eyeball it. It's a little bit more than 50%, or we could do it more precisely using our techniques for normally distributed variables. Here's a standard way to do this. So what we can do is we could write a parallel axis next to the x-axis. So here, this is our x-axis here. We're going to write a parallel axis right next to it, and it's going to be our z-axis. That counts the number of standard deviations. So, and this will be, the 0.42 translates to 0. That's the exact middle, the standard deviation. And then we'll figure out how many standard deviations we are from the mean, knowing that each standard deviation is worth 0.08. Okay? So, talk is cheap. Let's do it. So, parallel to the x-axis, I have a z-axis. This is called my z-axis. All right, in the middle of it, I have 0. Right here in the middle, I don't know what value that is. That would be the number of standard deviations there are from here to here. Well, let's think about that. From 0.42 to 0.37, how much is that? This distance here would be 0.42 minus 0.37. That's pretty easy to do. That's 0.05. So this would be negative 0.05. If not, you could do it on your calculator. Obviously, you don't need that, but what we're doing is 0.42 minus 0.37, like that. Well, no, not like that. The point there. Okay, so that's how we get this distance is 0.05. This distance is, let's change colors again. 0.05, just by subtracting the two numbers. What you want to do is you want to translate that distance. Oops, I shouldn't have written that here. what you want to do, you want to translate that distance into standard deviations. The way you translate that distance into standard deviations is you divide by this. How many standard deviations? It's not even one standard deviation. You would need 0.08 to be one standard deviation. This is 0.05. So the way we figure out how many standard deviations is we divide the two. So we go, okay, 0.05 divided by 0.08. How much is that? That's 0.625. Duh, that's 0.625 negative. Actually, we go with the purple color there because that's z-axis. So that's how you find the z-coordinate that corresponds to that coordinate. You can translate here by dividing the difference between them by the standard deviations. You might have seen it in the formula sheet. We also have a formula sheet that tells you exactly how to do this. It's probably somewhere here. Right here. To get the z-score, even before chapter 8. Chapter 6 stuff, normal distribution. All right. So what you do is you take the difference between the two and then you divide by standard deviation. This is how the textbook will suggest it. So in other words, the way I got that was that z is equal to the 0.42 minus, the 0.37 minus the 0.42 divided by standard deviation, which is 0.08. That's how we got the 0.625. Negative. Okay. What's the point of translating from x coordinate to z coordinate? The point of that is that we have a table that tells you exactly how much area there is if you know the z-score. If we know the z-score, we can figure out exactly how much area is there. This is this beautiful table here that tells you. All right, let me see where the beautiful table is. For negative z-scores, what you do is we're looking for negative 0.625. And when we find that spot, it'll tell us how much area is to the left of that. So I'm going to go to negative 0.625. So the way this table works is you're going to be looking at these numbers. These are the first couple digits of your number, and these are the last parts of your numbers. So for the negative 0.6, that will be the column here. And then the 2.5, that will be up here on the top. Okay? Or actually it only goes to one level, negative 0.2. So, and sometimes because the table doesn't have like infinite much accuracy, you might have to round off sometimes and find the closest number to it. So in this case, I'm going to go with negative 0.6. That's the row that I'm looking at. Negative 0.6. Okay, and then to figure out, I need a 2 or a 5, so I could round off to either one of these two. It would be somewhere in between there. So let's say we round up and we've used that one. So it's 0.2643. Okay, 2643. So this is telling me, but the way the table is set up, it's set up to give you the area to the left of that. So that area is 26.43% of the area. Now, the question that we wanted to know is what percentage are greater than 0.37. So we want to know how much area is over here. Well, if 100% of the area is here and 26% of the area here, obviously that leaves about 74% of the area there. So to get that area, what we're doing is we're taking 100% and subtracting the area that we don't want. The one that the table gave us, that would be this area. That would leave us with the area that we need. So the next calculation I do is 2643. So I got to remember that, 2643. So if I have that minus 2643, how much? It should be about 74%. Okay, 73.57. So that leaves 73.57% of the area to the right. So that together, these and this make a total of 100%. Now, the software that I wrote actually measures more accuracy than the table because I have some amazing programming skills. So So the answers may not fit exactly, but they'll be really, really close. Like that one's not close, that one's not that. This one is really, really, really close. So we'd go with F. Okay. Hope you find this helpful. See you guys on the next one.